Okay, over lunch today, people were bragging about how long that they've used Mathematica. I've actually used Mathematica since 1982, and you might say, hold it, that's impossible because Mathematica didn't exist then, but I actually used SMP, which was the precursor to Mathematica, and it basically had the same syntax as Mathematica. In fact, you just changed dollar signs to underscores, and the pattern matching worked as well. So anyway, what I'm going to be talking about is work that I did as a PhD student, which is now coming up to 30 years ago, which is a bit scary. But I've come to revisit it lately because some of the better tools in Mathematica have made me interested in it. And also, I've been teaching students, third-year undergraduate students, about this material because I think it's quite accessible to them using Mathematica. So I realize that'll be a bit small. Let's just enlarge this for a bit. So exact solutions to the Schrödinger equation for atomic and molecular systems have been sought since 1926. We have closed form solutions for hydrogen, which was the standard textbook example. And H2 plus, the hydrogen molecular ion, can also be, it's variable separable, and you can do a lot with it, but you can't write it down in a closed form the same way you can write down hydrogen, but you can do it in spheroidal coordinates. What has been known since the 1930s is essentially that if you try and solve helium the same way you solve hydrogen, and I'll define these interparticle coordinates, R1, R2, and R2 in a second, if you try and solve for the wave function of helium using these coordinates, you find that it fails. And I'll prove that to you today that it fails. And what the reason for that failure is interesting, and the solution to that failure is also interesting. And it has consequences not just for helium, but for every atom and all molecules as well. So it's an important consequence. In other words, we can say that the wave function is not analytic. There's no Taylor series. Hydrogen has a Taylor series solution. Helium does not. No other atom or molecule does. So it's an interesting consequence. However, we do know, it's a postulate of quantum mechanics, but we also have now theorems to prove it, that the wave function is finite and continuous for these coordinates. So we know something else about it. And even though I'm not going to show you the full solution today because it doesn't exist, but there is steps towards it, I think the steps actually give you insights about the structure. I have a colleague who is a quantum chemist, and most of the problems he sees with quantum chemistry is the fact that the molecular programs fail to reflect the interparticle coalescences. When electrons coalesce, there are cusps in the wave function. They are energetically important, and a lot of the geometry and energies that we get for these systems are flawed unless you reflect that behavior correctly. So we'd like to improve variational basis sets, get better expectation values, and so on. And an exact solution is the sort of thing we need to be able to do that. So let's just revise. This is, say, second-year undergraduate stuff in Australia that we learn. We have the wave function for hydrogen written in the sort of standard way. We have a radial part to it and an angular part, and we use separation of variables. And what's nice in Mathematica is, of course, well, we can, one nice thing is we can prove that it's analytic. We can just do series expansions on these things and see what's going on. And even though we have Laguerre polynomials with arbitrary indices there, Mathematica can handle this for us quite nicely. But we can also do plots. And the nice thing is we can see both the symbolic form, the solution, and we can change the quantum numbers n and l and see what's going on. So immediately we have, this was used to be a table in all of the textbooks, but we've got a more interactive version of that. Another thing that the students have to get introduced to is the spherical harmonics. And what we have in Mathematica is the ability to visualize those. And let me just scroll down here. One of the nice things, I'm using this feature of Mathematica more and more, is the fact that you can use a tooltip. You can wrap a tooltip around your graphics, so the symbolic form for each of the spherical harmonics is popping up. And here we have a table of the S states and P states and the D states and the F states, and our colouring is using a coding of the complex plane to represent what's going on, the phase information there. So we can do much better plots than most of the textbooks have, and the student learns something, I think, in coding those too. Well, that's a very quick review of hydrogen. What about the hydrogen molecular ion? Well, we set up a system of coordinates for solving this, and we use these confocal elliptic coordinates. The equation, and this is another feature, I don't know if anyone's used this, but what you can do, again with these tooltips, is you can wrap tooltips around parts of equations, and this is popping up showing it's the potential, the energy, and the kinetic energy part of an operator. And I think that's a nice little thing, that you have these bits up, and over here's the wave function. So I mean, you could do much more than that. I'm just showing this as a simple example of that. We can, of course, visualize it, and what we can see there, this is essentially a ground state of the hydrogen molecular ion. The 2 points there are the location of the protons, and we can see the cusp behavior there. Clearly there's a discontinuity in something, a derivative discontinuity around those 2 points. And so that's the cusps that we get in the wave function. Another feature is, what is the energetics of this system when we have small, as our distance is approaching 0? You can be shown, and I had a student extend this, and it's quite a bit of work to algebraically extend this, that the energy of the hydrogen molecular ion as a function of distance starts off as a power series, but when you get up to the 5th order, logarithmic terms arise in this. And that's the typical analytic behavior. And that type of analytic behavior will come up again later. This is actually known now to much higher order, but it's actually still rather difficult to generate terms in this. The asymptotics for large separations are actually even more mathematically interesting than the low order states, but I won't cover that here. So now the focus of my talk is just to give a bit of an overview on helium and the sort of things that have done and still doing in it. First, if we're teaching students, we've got to give them a bit of a background. Here I'm showing the coordinate system that we're going to use for the ground state, which is a spherically symmetric state, the S states of helium. And because they're S states, even though this is a 6-variable problem, it's a 6-variable problem because we assume that the nucleus is fixed, the 2 electrons are free to move. So we've got a total of 6 variables to describe this system. But in fact, we have a plane, the triangle formed by the 2 electrons and the nucleus is forming a plane. And we have 3 Euler angles to specify the orientation of the plane and 3 internal coordinates specifying the dynamics of what's going on. And our problem reduces down from 6 dimensions to 3, and it's a little bit more manageable. But I just wanted to show you that as you move either of the electrons, you can see what happens to the internuclear separation, R12, the distance to electron 2 and the distance to electron 1. And over here I just have a table of those coordinates, and I'm also showing some of the other coordinate systems that are used to describe this problem and what happens to those. I'll explain a little bit about them in a second. But so we get an idea of how the angles and the distances change when we manipulate that. So I showed you the Hamiltonian and the Schrödinger equation for the hydrogen molecular ion. The Hamiltonian here for helium has the kinetic energy part here, the potential part here, and the energy part. And one of the crucial features of it is the dimensionality of each of those parts, and I'll mention that in a second. So H is the Hamiltonian, T is the kinetic energy operator, and the important feature of that is it's homogeneous of degree -2. If you give it r to the n and you differentiate twice, you get r to the n -2, and that means that this operator is homogeneous of degree -2. The potential is homogeneous of degree -1, and the energy is a scalar, it's homogeneous of degree 0. And that turns out to be important in the method that we use to attack this problem. We then need to define the Laplacian. What is that operator in the coordinate system that we have? So we define the Laplacian, and that's what the Laplacian looks like. It looks a bit a bit of a nightmare, but actually some of these terms, like that term there, is just the cosine of one of the angles in that triangle. So it's actually not as ferocious perhaps as it looks, and that's the cosine of the other. And this sort of operator would be familiar from hydrogen. In fact, that operator there and that operator there are the radial parts for the two hydrogen atoms if there was no interaction between the electrons. So we define the Laplacian, and we can generate from this Laplacian some examples of what are called hypospherical harmonics. A constant is a hypospherical harmonic. Certain geometrical combinations, r1 squared, r2 squared minus r1 2 squared, which is a symmetric function, and r1 squared minus r2 squared, which is an antisymmetric function, are solutions to the Laplacian operator, and they in fact generate the excited states for the helium atom as the starting point for all of the excited states. And it turns out, I'll show you later, we need some more complicated functions which are those hypospherical harmonics multiplied by certain logarithmic terms, and when you apply the Laplacian to them, you get rather simple results coming back. You get the same hypospherical harmonic divided by r1 squared. I'll explain a little more how they come up in a moment. The potential is straightforward. Well, first we define the Coulomb potential. We have the Coulomb potential for electron 1, electron 2, and the interaction potential for them. And we can show that the potential is homogeneous of degree -1. We use the definition of homogeneity, so we scale each of the coordinates by a factor lambda, and we show it's the same as having a lambda -1 on the other side. So homogeneity is easy to see. And if we now try and do series expansion, we'd like to solve this problem and say, can we write the solution as a triply infinite sum in powers of R1, R2, and R12? And we define K to be I plus J plus M, and that is the homogeneity, the degree of the homogeneity of our solution to the problem. And we can solve through looking at the Schrödinger equation, we can try and solve this in order of increasing K. So if we try and do that, introducing K has advantages. EV and T are homogeneous of degree 0, -1, -2 respectively. We can look and we can solve in different coordinate systems, and what we have to do is just match solutions by their homogeneity, matching K, and we can actually solve the equations in terms of determine the solution in terms of functions of increasing homogeneity or increasing degree, and the Schrödinger equation just becomes this, that the Laplacian acting on psi k, we have a recurrence equation which involves the potential and solutions that we've already done. So solving the Schrödinger equation reduces to solving this recurrence. Now, if we define an operator that uses this, by the way, I suggested to Jason to add this in, and it's been added in for a few years. Hardly anybody uses it, but you might have seen it there. That symbol is not an arrow, it's an arrow with a T arrow, and that is a shorthand for the function notation. So this is an operator that takes psi and acts on it. And I prefer that to using function or hashes and ampersands. It's the mathematical notation. Why not use it? It's built in. It works in standard form too, so I would recommend that. So we define the Schrödinger operator, and now we can, to determine the recurrence equation, this is easy. We act our Schrödinger operator on the generic term of our triple sum. So we get rid of the summations, we act on that, and that's what we get instantaneously pretty much. Pretty straightforward there. And to determine the recurrence, I'm just using pattern matching here. That pattern will take you a little while to digest, but it's basically saying do the manual operation you do by hand for recurrences, but using pattern matching, so it's a one-line command. And if we do this, we immediately get the recurrence equation for our system. And it's pretty straightforward. And what we can find or see is that this links lines of different k plus 1, k plus 2, and we can solve the recurrence in a standard way. We have some boundary conditions, and one of those boundary conditions is all the coefficients are 0 if the exponents are negative. Right? We don't want 1 over r1, because if we had 1 over r1, it would lead to infinities in our wave function, and our wave function is finite and continuous, so it can't have that. So let's try and solve the recurrence equation. Let's try and solve for k equals 0. We want the Laplacian acting on our first function to be 0. So we know how to solve that. They're the hypospherical harmonics, the generalization of spherical harmonics. And the first solution is just the constant. And we can choose it to be 1. So we'll choose the first solution to be 1. And we'll say our constant C0, is 1. So we can do that. Now let's try and solve it for k equals 1. And if we do that, and we generate a table of the recurrences, we get a system of equations. We solve for those equations, which is straightforward. Get the coefficients, and we determine the solution. And there's the solution to first order, which we can define. So it's simple. It's got 1, which is k equals 0 line, and the k equals 1 part is really simple. Right? It's just a monomials in those variables. It's trivial. If we exponentiate that solution, well, the problem with that is it won't be finite for all values, but we can exponentiate it. That is, we can consider this exponentiated version of that, which if you expand it in a series gives you the same series. That simple wave function, for example, if you want to prove that H minus has a bound state, that wave function is good enough to prove that. And that's actually, you can't do it with Hartree-Fock. It's quite hard to do with that other system. So this is nice. It's a very simple wave function. And there's a few exercises if anyone's keen. I won't cover those now. But the problem, and this was known by 1935, the problem is you can't solve the next equation using a power series. If you take your recurrence equations and you substitute in the solution you've already got, you get these two equations. And by eye, most of you will see that they are going to be inconsistent, but I'm lazy. I use Mathematica to reduce that, and Mathematica says it's false. There is no solution. So we know there are no power series solutions to this equation. So lots of people tried. Bartlett in 1937 was the first one to realize that this failed. There's been a whole bunch of attempts. Various people have tried ways around that problem, but they all had their own various problems. But Fock, who's famous for Hartree-Fock, in 1954 and translated in 1958, solved this problem. And his solution is that the expansion has to have logarithmic functions of the hyperradius, and the hyperradius is essentially the square root of r1 squared plus r2 squared. And if you include those, you can get nice solutions. It's essentially a generalization of Fuchs' theorem to partial DEs, and it's been generalized to molecular systems as well. So what does the Fock expansion look like? Instead of, we used to have 3 sums, we've got to add a 4th one here, and we've got to include some log bits. Right? So that's the generalization, and now we can solve the problem successively. However, well, I won't mention those comments, I don't have time. But if we solve it, we can actually find what the next term is. So this is what we had before from the power series solution. This bit here is the next part of the solution, the second order solution. And you can go to higher orders, but you get elliptic functions and some rather messy bits coming about it. But the approach that I've got a student currently working on is not try to get closed form expressions, but just use series in certain coordinate systems, and it's actually working really nicely. And we can solve essentially to any order we want to, and Mathematica is the ideal tool for that. That doesn't look too severe, but I'm hiding some complexity here. S2 and S1 turn out to be solutions to Laplace's equation that have got discontinuities, yet the discontinuities cancel out when you combine them in the right way, and they, if you want to look at the definitions, S1 is a fairly messy combination. S2 is an even more messy combination. It involves things called Lobachevsky functions, which you probably haven't heard of, but the Lobachevsky, the second derivative of the Lobachevsky function is tan x. So they're double integrals of tan, right? That's all they are. And so you have these 4 Lobachevsky functions in terms of alpha and beta are combinations of those coordinates. Sine alpha is defined by that, and beta is defined by that, so there's some definitions there. But we can proceed to higher and higher levels using this. So these solutions can be carried out. They remove the cusps. They're what we need for more accurate wave functions, and they've been used in variational methods and have improved things. The Fock expansion has also been proved mathematically to converge, so it's a useful expansion. And we're trying to find different coordinate systems. I won't spend any time on this, but you can read it for yourself. There's different coordinate systems which have certain advantages for doing the expansion, and one of these coordinate systems was used to find highly accurate variational trial functions and solutions for helium. So it's a promising line of attack. And I'll skip through those for time. You can look at that thing. I'll just make my conclusions. This expansion, which requires these logarithmic terms in terms of the size of your system, is ubiquitous, unavoidable, and any atomic molecular system, if you try and do it analytically, you'll require that. The solutions are complicated, but I think we're never going to get a closed form exact solution. I'm pretty confident of that. But series solutions to arbitrary order, I think we can get in these coordinate systems, because we can invert that recurrence for the Schrödinger equation, that Schrödinger operator, in a fairly straightforward fashion. It still requires some work. I think using computer algebra is the only way to do this. And there's problems if some people have a goal that they'd like to see a closed form solution. I don't believe it exists. Resumming is tedious, but certainly when we have done any of those closed form expressions were derived using SMP, which was the precursor to Mathematica, and people have extended them since then. And I believe now Mathematica is so much faster and more powerful, and there's other tools in it, that it's a good time to revisit this problem because we've got better tools to handle it. The one thing that I haven't dwelt on here is that this series solution is well defined and converges, but the problem is you still need to match to the asymptotics for large distances, and that's sort of the hard bit. At each layer, when you get the Laplacian operator, you get another family of solutions emerging, and you have to choose all of those arbitrary coefficients correctly to make the whole solution normalizable and to match the boundary conditions at infinity. And that's the hard, there's a PhD project in there. In fact, my PhD project was meant to be on that, and we decided after a year it was too hard, and so we worked on another part of it. So that's a real whirlwind tour. That the notebook's there, and you can read it in your leisure. But I just wanted to give you an overview of the sort of things that have been done using symbolic algebra there, and just a few ideas. I said I use this as a sort of like a teaching example. I gave this notebook to a third year, and by the end of it, with little work, he was doing the series calculations himself. So I think it sort of empowers students to get them up to speed in a topic really quickly, and that was very useful to me. So I'll stop there.